So I've written on the board where we left off with scalar model A. This is scalar model A with a single Onsager coefficient. In the Gaussian approximation, I neglect the nonlinearity of the model. So I arrive at a linear theory. That linear theory has correlation functions that we can calculate. And the simplest we already did. This is the static correlation function just coming from the free energy itself, no dynamics yet. And the static correlation function has this Ornstein-Zernike form showing that it diverges in the limit of t going to tc and wavelength going to infinity or wave vector going to 0. That is, this system shows criticality at tc. And now let's look at the dynamics. And for dynamics, we can look at various types of correlation functions. And to start out with, let's look at the simplest. So let's just look at the equation of motion that we have here and average it over the noise. So that's a noise average then. As we average over that noise, we find this is minus L R plus CQ squared phi of Q and T averaged over the noise plus 0 because we assume that the first moment of the noise is identical to 0. That equation is a simple ODE, which is solved by an exponential decay. So phi of Q and T is a constant, so it's proportional to the exponent of minus T over tau Q with the relaxation times tau Q given by 1 over L R plus C Q squared. So it's basically the same as the correlation function, and that means that this time scale also diverges in the limit of going to Tc or the limit and the limit of going to long wavelength. And this is known as critical slowing down. Just meaning that relaxation times become infinitely long and the dynamics become slower and slower and slower as you approach the critical point and as you go to long wavelength. Let's look at the dynamics a bit more in detail and introduce what's called the response functions, also known as dynamic susceptibilities. That means sensitivities to external perturbations. So recall how we wrote the equation here. And now let's say that in addition to Fourier transform in space, we also introduce a Fourier transform in time. So we already have phi of Q and T, and now we additionally perform a Fourier transformation in time. Then the dt that you have here becomes a minus I omega phi of Q and omega equal to minus L R plus C Q squared phi of Q and omega plus the external field plus the noise. And for the noise correlation, if I write it fully in frequency and momentum space, this is then C of Q and omega and Q prime and omega prime. Averaged is 2LT, 2 pi to the D, delta Q plus Q prime, and 2 pi delta omega plus omega prime. Now these equations are easily solved because now it's all just algebraic equations. There's no differential operator here anymore. And I can just collect terms on one side of the equation. So for example, I can collect all the terms of phi on one side. And I can ask myself, what is the average of this phi? Well, put this on this side, then you have a prefactor, which is minus I omega plus this one here. That's equal to LH. As you take the average, the theta is 0. So this is proportional to H of Q and omega. And there is a function in front of it, which is called the response propagator G naught. And this G naught is just the numerator from the left-hand side. So it is equal to 1 over minus I omega plus L R plus C Q squared. The linear response function, chi, of its arguments is defined as the response of the average field to the external field. So by definition, it is d phi with respect to dH. At external field equal to 0, and that is L times G naught of Q and omega, Q vector. All right, so when you write this out, this is then 1 divided by minus I omega divided by L plus R plus C Q squared. And this is the dynamic susceptibility, or the response function. And you see that this reduces to what we already calculated in terms of correlation function if I were to put omega to 0. So chi at Q and omega equals 0 is called the susceptibility, chi of Q. And that's simply this Ornstein-Zernike form that we had before. It's just missing the factor of kBt, but that's due to the fact that this is a response function and not a correlation function, and between the two there is a factor of kBt. That's the static limit. In general, as you look at this, this is a complex function. So we can split it up into a real and imaginary part. The real part is usually called chi prime of Q and omega. And the imaginary part is indicated by chi double prime. And you can write it out, and then we'll sketch it out on the board. The real part has the structure r plus c q squared in the numerator, and omega over L squared plus r plus cq squared in the denominator. So you see this is an even function in omega because of the squares. And when you look at the imaginary part, it has a similar structure, but it's now odd in the frequency. So it's omega divided by the kinetic coefficient, omega divided by L squared plus r plus c squared. Let me now draw it for you. He prime for a fixed q has a structure, right, that has a certain width defined by this q-dependent part, and the omega dependence is even. So it looks something like that. And as said, the width of it is determined by r plus c q squared. And when you look at the imaginary part, it has a similar structure, but now odd. So it's looking something like that. That's chi double prime of omega. And these are typical structures for response functions, and they're real and imaginary parts. Now let me go to the correlation function. That's a bit different than the response function. Here in the response function, we have been asking, how does the typical or the average value of the field respond to an external perturbation? So you tweak the system and you watch it relax. And we watch it relax here in Fourier space, looking at real and imaginary part. And now we ask, what about if we don't tweak it and just look what thermal fluctuations do to it? So what are the correlation functions for h equal to 0? So what are those? So we put h equal to 0. And then we again use the same equation of motion that we do have here on the board. So here is the equation of motion in Fourier space. Again, I shift all the terms with phi to the left-hand side. So that gets the inverse propagator as the prefactor of it. I put h equal to 0, so I don't have that. And on the right-hand side, I just have zeta. To calculate the correlation function, phi of q and phi of q prime, omega prime, averaged. As said, I get the propagator twice. This is then g naught of q omega g naught prime, q prime omega prime. And then what's remaining is the correlation function of the zetas. Those correlation functions, we also know they are given by their corresponding white noise expression. So there are these prefactor 2LT, the factors of 2 pi, and the delta functions that you have. So this is then times this correlation function. Let me write out 2t L 2p to the d delta q plus q prime 2 pi delta omega plus omega prime. Okay, and that object here, because I can put this q to minus q prime, q, and that here to minus omega because of the delta function. This I call or define as my correlation function of q and omega. And as you collect the factors, this is the 2TL divided by omega squared plus L R plus C squared and the square of that. So it's basically the real part, or related, let's say, to the real part of the response function. I come back to this in a bit even more carefully. So that's my correlation function. It's also instructive to look at this in time space. So we do the inverse transformation such that we get the correlation function as a function of time. So I need to do complex calculus and calculate the residues as I integrate over the right-hand side. And then you find T over R plus C Q squared times e to the minus t over tau q. And tau q is as I defined it before. So it's these time scales that we have here, 1 over L R plus CQ squared. And at t equal to 0, this reduces to t over R plus CQ squared, and that's our static correlation function that we have calculated above. So here we have it. This is the static correlation function to which it reduces to once I take equal times, which it must because it's defined in a same way. Now, there is one relation which seems striking. So let us do that here. If you look at this part here. That's the imaginary part of the response function. And just look at what it is when I compare it with this expression. It has the same denominator, right? But the numerator is different. What you see, what you get from that, just for this calculation, is that this is 2t over omega chi double prime of q and omega. And it's something that we have calculated to a Gaussian approximation. It's not an exact result, it's an approximate result, but it's true in the harmonic theory. The point, though, is that this is true in general. Okay, so for this theory, in general, and for a much, much broader class of systems, there is a one-to-one relation between correlation functions and response functions. And the relation between correlation and response functions is via the temperature, which is the prefactor that connects them. And here you have a factor of 1 over omega. This is also called a fluctuation dissipation theorem. And ultimately, this fluctuation dissipation theorem has the same origin, with the same origin as n equals 2LT. Because that comes from detailed balance and the fact that we approach a thermodynamic equilibrium state. Here, this is also connecting fluctuations and dissipation, which is here the response function, the imaginary part. And as said, it's a very general relation that one can show. I don't do this here, but you find it either in my notes or, if you like, there's a fantastic book by Kubo on statistical physics. And these are the volumes 1 and 2. It's a classic book on StatMech, and it discusses quite at length linear response theory for classical and quantum cases, and that's where this relation comes from. It's again a relation that's true in thermodynamic equilibrium. There's a temperature here. Right? This is not true if you are not approaching a thermal equilibrium state, and if you're not close to thermodynamic equilibrium, then you don't have this relation. And the way you typically see this in measurements is you measure the response function, which you can do by certain methods in a magnetic system, by some spin resonance experiments. And you can measure the correlation function by doing neutron scattering. And then you compare the two. You take the ratio of the correlation function and the response function and multiply it by omega. And then you have to get a constant. And this constant is a temperature. And if you don't, then either your experiment is wrong because you've done something that's not proper, or you have to say, well, the system is not at thermal equilibrium, there's something else going on. Questions? Good, then let me conclude in the last 10 minutes with model B. No. Yeah, let me do this. In model B, what's different is that your field phi, and for simplicity, let me now take a scalar field phi. This field phi is a density corresponding to a conserved quantity. So for example, this phi could be the density of particles in the system or certain molecules in the system. Then there's a conservation law, namely that the total number is fixed. And that means that if you have a dynamic equation for this conserved density, it must obey a continuity equation. So it's minus the divergence of the current of x and t. J of x and t is the current that corresponds to that density. And you know that, right? If you integrate this over a whole domain, then this can only change if particles flow in and out. If the domain is closed, this leads to particle number conservation. So this then means we have to write something for the currents. If we were to study diffusion equations, right? So let's say you have dTc of x and t, and c is just Brownian particles, and it's a gas of Brownian particles, you would just write Fick's law. This is minus d times the gradient of the concentration. Because gradients in the concentration then even out the density distribution. So in total, if you look at that equation here, you do get dTc of x and t equals d Laplacian of c and x and t. So simply the diffusion equation. And this law by Fick is one of an example of a relation which connects a current with a gradient of a quantity. Here, in general, I can also ask, what should I do here? What kind of gradient should I write in general that drives currents? So what do you know about a thermodynamic system? A thermodynamic system has a chemical potential, which is the gradient of the free energy with respect to the density. The free energy has to go to a minimum, and that means all of these chemical potentials must be spatially homogeneous. They must be uniform. Okay? So the gradients driving the flux of a current must be gradients in mu, okay? Because in thermodynamic equilibrium, mu is a constant. So that's the logic. You write this as a gradient, as minus a gradient in a chemical potential, and you write this in terms of an Onsor coefficient, which I make here in general dependent on the field phi. And so is mu, where mu is given by the gradient in the free energy. That's a typical assumption you make in what's called linear non-equilibrium thermodynamics. You assume that the currents driving the system back to thermal equilibrium are proportional to gradients in the intensive variables that create the deviation from thermal equilibrium. That's the assumption that you make, on which you then base the analysis. So model B in total is then what I have on the board. And let me write it out again. The current J of x and t is minus a kinetic coefficient times the gradient of mu, which also depends on space and time. And something that I need to account for as well is that this system, as all the other systems, has some kind of noise that drives the system back to thermodynamic equilibrium. And I need to calculate the noise. And I assume that the noise that we have here, it's a vector. This noise has Gaussian correlations with a variance that's given by a noise amplitude that also can depend on phi delta alpha beta delta x minus x prime delta t minus t prime. So that's now model B, and the difference is really the fact that you have a conservation law, but the logic is the same. Gradients in the free energy and spatial gradients here in the chemical potential, they drive the system back to equilibrium. What would you find? That's something you do in the problem sets. So what do you find for N versus L? No surprise. N is 2LT, and including the phi. So it's really N of phi is 2L of phi times T. You can show that in general, like I wrote it, in a way where you use the Fokker-Planck equation. You cannot show this with a full dependence on phi using this reasoning based on linearization, because there you need to linearize and you end up having here constant n of phi 0 and L of phi 0, which are the equilibrium values. Okay. So here it actually becomes necessary to go this different step via the Fokker-Planck equation to show that this is the case. All right, so let me stop here and take your questions and then continue next week with Model B.
We say compared to Model A, where A is driven by the function, like the functional, and here it's driven by the non-potential.
Yeah, in both cases, it's the chemical potential that's the driving force. The difference is that in Model A, relaxation is locally at each point in space. The system goes to the minimum of the free energy. And that's what this model describes, is dt phi is proportional to gradients df d phi. So it wants to go locally to where df d phi is 0. And that's possible if there's no conservation law. If there's a conservation law, then you can't just go to something locally, because you need to redistribute the density in space to achieve that. You cannot create or destroy particles. You have to shift them from somewhere to somewhere. And shifting them from somewhere to somewhere means there must be a current that drives density changes. That's what the continuity equation means. And now you have the question of what is the current. You need a constitutive equation for the current that tells you how it is driven back to a steady state. And there you start arguing heuristically. Okay? It's not strict here. This is based on saying, well, if you're close to thermodynamic equilibrium, then what makes you go back to thermodynamic equilibrium is the tendency of chemical potentials becoming flat in space and time, especially flat in space. So the currents should somehow be related to those gradients in the chemical potential. And now you say, let's take a linear assumption and take only the leading order term, so the leading order gradient, and multiply that with a kinetic coefficient that describes how it relaxes back to equilibrium. That's the idea. Okay, so local relaxation to equilibrium if there's no conservation law, and redistribution of stuff via currents that are driven by gradients in the chemical potential.
But can we see from the order, for example, here is the first derivative of free energy to the phi. And here is the second order, or third order of the same thing.
Where are you, Ming-Chi?
Yeah, the first line of the first one.
Here?
No, the first line. Yeah, here.
Yeah.
So here is the first order derivative. And here it can be like.
Yeah, that's the point. That's what comes out. That's the consequence of here relaxation is local. That's what this means. And the Lyapunov function goes to 0 locally. And that's not possible if you have a conservation law. You can't do this. Because if this would be what you want, you need to be able to create and destroy particles locally in space. Right? That's what I meant when I said you need to use symmetries and conservation laws. Symmetries give you the structure of the equations, the structure of the free energy functional, But the structure of the equation is heavily determined by conservation laws. Yeah.
But there's a difference in what is conserved, right? Here, obviously, F decreases, so free energy is not conserved over time at all, right?
Certainly not.
Certainly not. But here, what we're conserving is not the free energy. We're conserving
No, of course not.
Or over phi.
Yeah. What's conserved here is that the total number, or mass, let's call it mass, is the integral over phi over space over omega, and m dot is 0.
And that happens as soon as everything in my time evolution is in form of a continuity equation, right?
Yes, like Brownian particles that you have in space, right? They are not destroyed, they are not created. They need to reorganize in space, and there you have a conservation law.
And so the currents basically are not arbitrary, but here we have the gradient with respect to mu. Can we use something like the gradient of the energy?
No. The analogy is the driving force is the tendency of the system to go back to thermodynamic equilibrium.
And that sounds like here, right?
So here it's the local relaxation to a free energy minimum. That's in the non-conserved case. In the conserved case, you need to worry about the gradients in space, because that's what's driving the motion. Here it's just the system tries to minimize locally its free energy. If you have a conserved quantity, you need to change spatial gradients. So the best example is really this one here, where you have, say, lots of particles here, just a few there. So you have a gradient in concentration, and that means there's diffusive flux that tries to even out the particle density in space. That's Fick's law. And it says that the current is proportional to gradient in the concentration. And all this does here, it is generalizing that idea to a problem which has a free energy that's not just entropy. You get this, by the way, so you can try this for yourself. If you take for F, so take F equals ddx rho ln rho minus 1 and calculate mu df d rho, then you'll see that this leads to Fick's law.
So then mu is like rho, and then
Mu is then, in this case, is like rho.
and then the gradient of rho.
So you can check, right? If you do derivatives here, then you can check that this works out.
And then the additional spatial gradient gives me Fick's law.
So Fick's law is then just the gradient of mu, which is, gradient of rho. And what is contained here in addition is changes in the chemical potential coming from the interaction. Remember our Brownian particles that have a pairwise interaction, there the function f is not just rho log rho minus 1. It's rho log rho minus 1 plus the pairwise potential, and that then gives additional driving forces.